Okay, let's start our today's topic. Okay, especially I'm talking about, let me see, what do we say, arch and gauge model. Okay, and I think this is especially useful for financial um, assets. Okay, and most of the time we are looking for or study the rate of returns. Okay, and last time I think I explained the data set. Okay, which is something like this one. Okay, this is the data set for euro dollars against ECU against US dollars. Okay, and this is all the foreign exchange rate of ECU from 2000 to 2008. Okay, so we have more than 2,000 observations. Actually, I think I have the data set here is up to 2,355 observations, okay, which is from the first day of the January of 2000 to 2008, sometimes 2008. I think maybe it's in May, okay, all right. And this is all daily return, okay, it's daily return. So all this data is from, this is the first day of 2000, the first day of the 2000. I'm not sure, maybe it's not January the 1st because it's a holiday. Usually the foreign exchange rate will provide it 5 days a week, okay? So there's some, if there's a holiday, then we don't have foreign exchange rate, okay? So this is, so the first day of 2000 up to 2008, okay? And last time I think I mentioned that usually we'll take the log of the foreign exchange rate, okay? The reason we take log is the difference of the log is much similar to the rate of return. Okay, so actually is if I have the rate, okay, this is EX, right? Okay. This is the EX. Okay, so if I take the log of the EX, it becomes to log EX. Okay, so if I have the, so the first one, 1.1812, and the second one will be 1.176. 1.176. So the rate of return, daily rate of return, will be using 1.176 minus 1.1812 divided by 1.1812. Okay, so this is something like, if I put this is A and this is a B and this is B, so something like A over B minus 1. Okay, so if I take the log of each one of them, it will become to the log A and the log B. Okay, so this is similar, like I'm taking log of A over B minus 1. Okay, so log A over B is equal to log A minus log B, but since this is minus 1, and actually the natural log of the 1 is equal to 0, but actually it's not, using this one minus 1. So it's pretty similar. This is similar to using log A minus log A minus log B. Okay, so that's why we're using log of the original foreign exchange rate. Okay, then take the difference. Then it becomes the rate of return. Okay, this is the reason why we take the natural log. Okay, all right. So I need another one which is called D1, which is the difference of the natural log. Okay, all right. So this is rate of return. If I take the difference of the natural log of foreign exchange rate, it becomes the rate of return. So I'm studying the rate of return. Okay, all right, and so let me explain that the return. Okay, how do we measure the variability of the return? Actually, return is just a variable x, if we call it x. Okay, how do we measure the variability of the x? Most of the time, we are studying variance, right? How do we get the variance? Variance of x is equal to what? What's the formulas? It's using xi minus x bar squared. If it is sample, then over n minus 1. This is the variance. Okay? So we say that the variance is just only the one single numbers which measure the sample size. Okay, so actually I have this 2,355 observations. So variance just look at the standard volatility, but it doesn't count the past information. Okay, so if I do have those data, it's not that smoothly, and I do have some period of time which swings, wildly, but some period of time which is pretty calm. So variance is not able to measure those volatilities which sometimes is pretty swing, the other time is pretty calm. Okay, if we can consider the past information of the rate of return, then we will know the actual volatility, including, which is very severely swings. The other one is pretty stable. Okay, so this is what we call unconditional. This is what we call unconditional variance. Okay? So if we thinking about another one which is conditional on the previous information of the rate of return, and it becomes the other measures. Okay? And this is what this arch coming from. Arch means ARCH. Okay? Autoregressive conditional. Then what? Heteroscedasticity. Have you remember we learned heteroscedasticity? What's the heteroscedasticity? I mean, if we're talking about the matrix, okay, maybe those engineering students more can measure using the matrix. Okay, if we're talking about the matrix, this one, when we talk about the heteroscedasticity in cross-sectional data, remember that? Okay, so we're using I. So the heteroscedasticity is the something which we talk about if I have n observations. So this is something like 1, 1, 2, 2, up to sigma square n. Okay? Then those parts, okay, off diagonal is something we say this is 1, 2 square. This is 1, 3 square up to sigma 1n square. Something like this one. Okay? So heteroscedasticity is talking about these parts. Okay? The autocorrelation is something like these parts. But autocorrelation can happen in this area if it is heteroscedasticity. Okay? So when we say the arch is saying that auto-correlated regression, auto-regression conditional heteroscedasticity. So they do have, this one is autocorrelated, also this part is autocorrelated. Okay? And this one, since we say autocorrelation, means we consider the past information as sometimes of lag. Okay? All right? So this is what arch coming from. Okay? So if it is conditional variance, so for example, return we are talking about is the D1. Okay? D1, okay, do have some relationship, if I can say, which is beta 1, beta x. Although this x, I'm using just x, but it can be more than 1x. Okay, so but for simplicity, I'm just using 1x. And we say that the model of this one, UT. Okay, if we don't have any heteroscedasticity, what is the behavior of this UT? Is what we call IID white noise, right? Right? This is IID white noise. But if we do have heteroscedasticity, what happened to this one? We say that this UT is IID. Usually we express in this way, independently distributed as normal distribution with mean 0, and the variance is like this. Okay? If this one doesn't depends on the period of time t, is equal to some certain constant, then this is called, we can use the normal distribution. And this is no heteroscedasticity. Okay? I think using this one, although it is math expressions, but easy to understand it. Okay? All right? But if this is not equal, to one certain constant, then it will depend on the t, or even depends on the previous t. Okay? All right? So, in other case, we are talking about when we say assets return, financial assets return, usually it doesn't doesn't like the usual IID with the white noise. Okay, you understand what I'm trying to say? Okay, so therefore, we are going to introduce the new model which called ARCH. Okay, so ARCH is autoregressive, conditional, heteroscedasticity. And in that case, my UT, okay, let me use the expression. So what I wrote it here. Okay, like this one. Okay, so for example, this is the one I'm talking about, the D1. This is the rate of return. Okay, if I'm consider the rate of return, actually here I didn't use any X variables because, what affect the rate of return is so huge. Okay, so I'm consider the model something like this one. Okay, then this is the diagram. Okay, look at this one. If I'm running the regressions, okay, then I will have something like this one. This arrow terms, okay, and using this arrow terms, and the diagram just look like this one. Then it means that for all the observation, this is for the time periods, right? From the first observation to the end of observations. And look at this diagram. It means that some periods is pretty swing wildly, and some of them is smooth. But most of the time, it really swings. Okay, so in that case, this is now something like this one. Okay, all right. So you can use your own data. Okay, would you please download the data EXLNX, which I already put in iLearning. Okay, let's see the diagrams, something like this one. Okay. In other words, if I'm using eViews, okay, I'll show to my business students. Okay, if I using the eViews, let's see. So I'm using the eViews. Okay, this one. Okay, I already have. If I import the EXLNX to the eViews, then I do have the variables, but I create one is called D1. Okay, so please create the D1 first, which is the difference. So how do you do that with the D1 in eViews? Just use the D, okay, then put the parenthesis of LNEX. So would you please do that too in your Pythons? Okay, the difference of LNEX. Do we need aircon? You may also take a look at the graph of the original LNEX too. Then take the graph of the D1. No, run the regression, then take a look at the, let's see. If this, I can view graph. This one. It's something like this one. This is the original LNEX. So this is what we call autoregressive. this is a chart of L and EX. And if we take a look at, let me see, what is this one? Okay, this is actually after I run the regression using just constant. Okay, and this will be the residuals and square hat. Then I square it. Okay, look at the variance. This is the variance of the residuals from the models of D1. Okay, so in eViews, I'm using, especially, okay, let me estimate. Okay, just D1 using, then I'm using OLS. Okay, if I'm using OLS. Okay, so I have the residuals, then what is this? Where can I, where is my original? I have the residuals, right? Oh, I think that this is this one. This one? Okay, I have the residuals, right? Using the model I just run, and I will name it generate square hat is the RESID squared. My hat. Where's the hat? Oh, yeah. Okay. Find it. Okay. Then I have this square hat. Okay. Then I can open it and see the graph, which is just like what I have it here. Okay. So if you look at the residual, I know that the variance of the residual is not constant. Okay? All right? All right. So in other words, I should look at the not only the model itself, which is what we call the expected mean of the model, but also consider their error terms, which is heteroscedasticity. Therefore, we're using arch model. Okay, so if we're using arch model, we can estimate not only the original model, we call them as a mean equations, as well as all the residual, the pattern of all the residuals. Okay? Okay, so actually, let me using some of the mathematical equations. Okay, so look at this one, D1, if I conditional on the previous information, okay, I may have this equation, something like the 3, okay, equation 3. But in this case, I didn't really consider any x variables because, I'm thinking that the rate of return is so many factors Therefore, I didn't consider this one. I just consider using the constant. Okay, but for the other studies, maybe you can put this some kind of important x variables in it to explain the mean equations. Okay, and look at this one. This is what we call the variance equation. The variance, if we consider the past information, so IT minus 1 is the previous period's information, then actually this is normal distribution with mean equal to 0 and the variance sigma t squared. So if the sigma t squared equal to sigma, this means homoscedasticity without heteroscedasticity. Okay, but if it is not on this some constant variance, then the model can be considered like this one. So this one is based on the previous u squared t minus 1. Okay, and actually this model is is proposed by the person who is called Angle. Okay, he proposed this model and he got Nobel Prize in economics. Okay, so this is very famous. The arch model is famous in economics. Okay, all right. So this is what the theoretical parts. Okay, and let me see. Okay, by the way, since this is the variance, actually the lambda 0, if lambda 1, okay, look at lambda 1. Lambda 1 is the coefficient of the past information. So in other words, if we test the hypothesis of the lambda 1, if it is not reject the null hypothesis, means equal to 0, right? This one equal to 0, then this one becomes constant, so which is no arch model. Then actually, if we're using arch model, this is reject the null hypothesis, means this value is, it's not equal to 0. Okay? But this is not equal to 0, but also what? Since this is a variance, so this one should be positive, since all the variance is positive. So remember, this one is positive. So if we use the estimation, we should see if we can estimate the residual variance model, all the coefficients should be positive. Okay? All right. So look at this one. So if I'm considered just the first leg, okay, so this is what we call arch 1, equation 5. So equation 5 is this one, okay? This one. If I just put the t minus 1, means that there's just one leg. So it's what we call arch 1. All right? And actually, it's easy to extend it to p periods. So which is something like this one. Okay, it's not only the t minus 1, but up to t minus p. Okay, but we will also understand that the higher order of the p means we need to estimate more coefficient of the arrow terms, right? Okay, so it will, the degrees of freedom will decrease. Okay? All right, so using these examples, so we're saying that if we have more than one lags up to p. So we need to also do the hypothesis testing of all this lambda 1 to lambda p, the coefficient. We have to test for that, okay? If we test for 1, we can just use the t statistics. If we are going to test all of them, we need to use the f statistics, right? So I think this one for all of you is pretty, you all understand it, that, okay? All right, then, so if we wanted to use the arch model, so how do we do it? Okay, so let's come back to our eViews. What we eViews do is, let me see, where is my, so I'm going to this one. Cancel this one. Okay, then, okay, I'll come back here. Okay, then I'm going to estimate the model, right? So this time, since my, I don't have any x variables, I just have y, okay? So I'm using, it's quick. Okay, I'm using quick, and I'm using the function of estimate equation. Okay, then here, type my D1. Okay, then constant. Okay, and this time, please do not use least squares methods, because we are estimate not only the original mean equation, but also the variance equation. So OLS cannot do that both. So we need to use what they already have it. This is called arch model. So do this function called autoregressive conditional heteroscedasticity functions. So this function, I can use arch or garch. Okay, so if I use arch or garch, all use these functions. And now my arch is from, okay, I'm trying up to maybe 4. Okay, or I can try 2. 1 is 4. Actually, the p, okay, actually the leg of p is really depends on, empirical study. It's really, it's hard to say that which p is suitable. Okay, we always need to try and error. Okay, all right, and so maybe I'll try. 1 is 4. The other one is I'm going to try 8, or I can try 12. Okay, but this is daily data. Okay, and in this case, the garch is 0. Okay, since I'm just going to use the arch 4. 4 means previous 4 periods. Okay, all right. Let's look at this one. This is what we call the arch model. So with this arch model, I not only estimate the mean equations, but also the variance equation. Do you see that? This is the mean equation, and this is called variance equation. And since I'm adding 4, the lag 4 periods. Okay, so what did you see? This is is this already? Okay, this one. So I can see from here that actually all of them are positive, right? The coefficient of all of them are positive. And how about the probabilities? Did you run this one using the Python? Okay, try it. do you have the function like ARCH or? Oh, okay. So maybe that works. So actually, if I'm using alpha at 10%, then, this is only the previous leg fourth is significant. Okay? You may try, 8. Actually, when I try 4, because I'm going to also talk about the gauge. Okay, gauge is more, it's pretty similar like arch, but it's more advanced, and it can be accommodate the higher order of the arch. Okay, so if I try leg is something like 8 or 12. Okay, so this is the, okay, I'm working with this one is Nemeth equation. First equation is the fourth leg. Okay, so let me try. So quick estimate equation. And let me try arch for 8. Okay, and arch 0. Okay, I can try 8. This is the 8, which means that, okay, started from 4th, it is pretty significant up to the 8th leg, right? So looks like this is more much better than the one just with 4 legs. Okay, so I'll name it the second equation, then I can compare it. And I tried the 12 to estimate the equation. Oh, arch order greater than 9 is invalid. So 8 is the maximum. Okay, all right, because it's really higher order of the arch can be expresses as a gauge. Okay, usually. So 9. Okay, I can try 9, right? Okay. So let me try 9. Okay. So number 9 is not significant. Okay, all right. So it seems that up to 8 is much better than to express the behavior of the residuals. Okay. All right. Good. So this is what we say, that if we find out there's a heteroscedasticity in our time series model, then not only the autoregressive, but also the heteroscedasticity. Okay, then we can use the arch model, which express better than just using OLS. Okay, actually OLS is not quite right because it cannot estimate all the variance equation. OLS just estimate the mean regression, which is this parts only. Okay, and since this one, we also need to consider the behavior of the variance, and which is not the IID with the normal, with the white noise. And we consider the volatility of the return, then arch model is much better than the GARCH, than the OLS. And I think all the theory behind is just like what I just mentioned it to you. Okay. And actually all of, like this ninth is become to negative, right? So it is not, it is not good. Okay? So up to eighth is enough. Okay, let me go back to the eighth. Did I have the eighth? Yes. I think I have the eighth. Cancel. Yeah, this is the eighth equation. And this is the fourth. This is the fourth, and the other one is eighth. Oh, cancel. Okay. This is the fourth, this is the eighth. Okay, I'm not sure whether, do you have any application in your area of this one? Okay, all right. Well, did you have this result using Python? A little bit different? I mean, all these numbers?
No, I think I did something.
I'm not sure. You know, sometimes if different, since they are using some of the programmers. I mean, I'm not quite understand how, but if you have the difference, it won't be very big. You know, if it is smaller, it might be okay. I'm not sure about it. I really didn't know that. Oh, okay, change the parameters by default. Yeah, okay. Actually, this one, you know, see this model, I really didn't try any other x variables. You know, if I have other x variables, I may try it. But in these examples, you know, since we're looking at the rate of return, okay, and actually so many events can be a factor of the rate of return. So I'm just using constant, okay, just using the mean, okay, without any other x variables. This is what I have it here. And the variance equations, I just consider how depends on how many lags I need to have my past information to forecast or to understand the behavior of the rate of return. And actually this one tell me that, you know, I can use up to the 8th order. Huh? Oh, okay. Because this one is using what we call maximum likelihood estimation. When they do the maximum likelihood estimation, they have to do try and error. Okay? So usually they will converge up to 8 iteration. Iteration means they have to do try, you know. This is not like the ordinary least squares methods. Usually, maximum likelihood estimator is not straight line. Is a very complicated. You need to using several tries and up to the converge. Do you have any better explanation of this one?
It's like a guessing.
Yeah, guessing.
So you have an initial guess with initial probability. Then after that, you keep that as your memory, right? Then you try again, and try to check whether those memories are the same. And if they're different, you try to do it another way. But if the difference between those two is quite similar, then you go in that direction and guess it, until you get a point where you have there's no difference. It's
Like a try and error. Just means converge it.
not in the model error, but between the guess and the trial.
The computer was using the initial parameters. Okay, using that parameters, then try to estimate it until satisfactory. What's the goal? I mean, the purpose for converge. Converge means similar, same. Less difference. Yeah.
Yeah, it's actually the same. Because the convergence there is the minimal point, which is also the minimal point of error.
So this means that they do after a iteration, just back and forth iterations, then they'll come out with the result. Only computer can do this way. Oh, it's impossible. It's impossible. Just out of law. Well, then all this estimation is stable. It won't affect. It's not that sensitive. They will estimate until they're very stable. Okay, and this is the final result. Like this one, they are trying 7 iterations. And they're starting with look at this pre-sample variance. The parameter is 0.7. Did you see that? The parameter is 0.7. So they'll try it, actually this very higher math. So I just cannot explain it, in the math way, in mathematical way, but I'm just using the intuitive thinking. Okay, let's have a break, okay?